It's not that hard. Hi! Here we go. We're going to find the arc length of this function. By the way, this is a function of x. What does that mean? It means if I put a different value from x, we get a new value out of that integral. Y is a function of x in this case. And we're going to remember, since this is in the form y is a function of x, that we're going to use the arc length formula from a to b of the square root of 1 plus dy dx quantity squared dx. Are you okay with that idea? All we need to know is what is dy dx. Well, how about we take this function, y is equal to the integral from 0 to x of tan t dt, and what if we take the derivative of both sides of this with respect to x? That's something that we've done before. We can do it again. Well, I'll do the left-hand side. That's dy dx. Okay, now you guys do the right-hand side. The derivative of an integral. They cancel out. So what's the answer? Do you remember this? This is fundamental theorem of calculus part 1. Tangent of x. The derivative of this function where the variable is the upper bound is you plug it in. If this thing is a function of x, you've got a chain rule on top of that. But essentially it's a plug and chug. That's tan x. That means we can come back to here and let's fill in the blanks. The integral from 0 to pi over 6 of 1 plus tangent squared, I should say tan x quantity squared dx. And lucky for us, what? Yeah. This is the integral from 0 to pi over 6 of the square root. Let me see if I do this right. I've got, I think it's tangent, yes, tangent squared plus 1 is equal to secant squared. Okay, so this is going to become the square root of secant squared. Or the integral from 0 to pi over 6 of secant. There we go. Now, analytically, can we solve that? Bless you. Bless you. I think we did this. I think we did this. Do we have a, is anyone at the solution management page just to remind me? I think we found out what the antiderivative of secant was at one time.
The solution rule always took the 1 away under the
Yeah. It's because it's factored
It's
in.
1 over cosine, so
Oh.
Expanded and then refactored.
yeah, so yeah, ln
It makes sense.
ln
When
equals
you.
1 over u.
So do you always just do
U,
it?
so
No, like,
ln
one over over here.
yeah, so this is 1 over
Square this out,
cosine,
boil it out, and then you add the 1 in, and then this is what it's square root.
and then this must equal
But I'm looking at this, I'm not, they say then, what's the B part of this question? Oh, just to graph it?
Yeah.
Okay, they don't ask for an analytical solving of that integral at all, do they? They just want the setup, do they?
They only do part C. They just want the answer.
Oh, the answer, yeah, okay. So they don't give any, I don't think I can do that analytically. It looks familiar, you would think that I would,
would
yes?
it be ln of cosine?
No,
Here's what I remember. I remember that the antiderivative of tangent x is equal to natural log secant x I want to say plus x plus c. Something like that. I know there's one for tangent. Because you use sine over sine and then you do a u substitution with the bottom. But,
I don't think it'll work.
no, I don't think that's an x there. But I don't think we have one for secant. I think at this point, you just plug that into the calculator. And let me do that. So get my calculator out. Let me see, alpha f2 4 from 0 to pi divided by 6 of secant, which is 1 divided by cosine of x. And we're going to do this with respect to x. And we get, that's the answer, okay. So, indeed, I want to, as many times as possible, solve these analytically, but sometimes it's just not possible. 0.549. And we'll call it a day on that problem. All right.